So, good afternoon, everyone. Sound going through okay? Can everyone hear me?
Yes, I can hear you. Can you hear me?
Okay. Yeah, I can hear you. Good. So let's get started. Good afternoon, everyone. So my name is Han Tao Chui, and I'm hosting this webinar for Professor Le Xie from Texas A&M University. So first of all, thank you for calling in this webinar. This webinar is hosted by the IEEE PES CAMS Subcommittee, Computing Analytics Methods Subcommittee, and Professor Le Xie's presentation title today is Massively Digitized Power Grid, Opportunities, Dangers, and Challenges. This is the fourth webinar that CAMS is hosting this year. About Dr. Le Xie. Dr. Le Xie is a professor and Eugene Webb Faculty Fellow in the Department of Electrical and Computer Engineering at Texas A&M University. He received a BE in Electrical Engineering from Tsinghua University in 2004, and an MS in Engineering Sciences from Harvard in 2005, and a PhD in Electrical and Computer Engineering from Carnegie Mellon in 2009. His industry experience include ISO New England and Edison Mission Energy Marketing and Trading. His research interests include modeling and control in data-rich, large-scale systems, grid integration of clean energy resources, and electricity markets. Dr. Xie has received the U.S. National Science Foundation Career Award, DOE Oak Ridge Ralph E. Poe Jr. Faculty Enhancement Award, and the 2017 IEEE PES Outstanding Young Engineer Award. He was also the recipient of the Texas A&M Dean of Engineering Excellence Award, the EC Outstanding Professor Award, and the TES Selected Young Fellow. He is an editor of IEEE Transactions on Smart Grid and the founding chair of IEEE PES Subcommittee on Big Data Analytics for Grid Operations. He and his student received the Best Paper Award at the 2012 North American Power Symposium, IEEE Smart Grid Com 2013, and HICSS 2019. He chaired the 2018 NSF workshop on real-time learning and decision-making in dynamical systems. Now, time is for you, Dr. Xie.
Thank you. Thank you for the kind introduction. And it is indeed a great honor and pleasure to present to one of the sort of sister subcommittees that I am chairing now. As you know, it was introduced earlier. There is a sister subcommittee to CAMS, which is called Big Data and Analytics. And we also run a fairly popular webinar series. So it's really indeed great to see that, you know, COVID has turned everything into the digital space. And actually there are, you know, very dynamic and very frequent information exchange across the professional society. So this is a work that sort of summarizes a lot of our activities in the past decades, and I try to sort of summarize them into opportunity, dangers, and challenges associated with the digitized power grid. So at this time, I thought, you know, we should really take a look at what's going on because of the COVID. So I'll first give you a very quick overview of some of the situations in the US power sector regarding the COVID, and then I'll give you a bit more longer-term view of what are some of the key trends that I see, and then I will share with you some stories associated with opportunities, stories associated with dangers, and some of my remarks about, you know, how do we align technological solutions with the appropriate market and regulatory frameworks to support this transformation towards digitized power grid. So this is something we have been doing in the past 3 months. Our students and myself and some collaborators, we took the NASA's, you know, nighttime image data that is taken every day from the space. And this is the city of New York. And what you see here on the left is the midnight brightness of the New York City on February the 8th. What you see on the right is the same time, but April 25th. After we take, this is actually something we post-process because we actually take out of the ambient lighting of natural lights. So I was literally shocked when I see this because this is a very visual indicator of the reduced human activity through the reduced the brightness of the city, right? So you can see the average intensity of the city actually got dimmed down by about 40%. And that is a very strong indicator of the human activity reduction, as well as the indicator of how electricity sector is affected. So, we have spent quite a bit of time in the past 3 months, and we actually built this open access and cross-domain data hub. Everyone is welcome to take a look at it. It's on my homepage. What we do is that we collect all the US regional market data on a daily basis. Every day we take the data. We also take the public health data published by Johns Hopkins. We also take some 45 million American mobile device data. Those are the indicator of the mobility of the society, as well as this satellite image data that NASA published. And then we try to sort of do some data cleansing and data quality control, and eventually trying to hope for some data-driven, science-based, policy makings as we're trying to get out of this mess. So it's still we're doing it on a daily basis, and you're welcome to take a look at it. Just to give you some very quick kind of a one-slide overview of some of the things that we can see, typical power system textbook would have never thought of public health as an indicator of the load forecast, but now we may have to, because as you see from the left, which is the epicenter of COVID in early spring and in the New York City, and what you see on the right is, as we speak now, the epicenter, Houston. Unfortunately, that's close to where we live, and you can see that there is this very strong correlation between what you see as the bubble size is the percentage of reduction of electricity with respect to the baseline, right? There's a baseline here. And then x-axis is the daily new confirmed cases of COVID, and y-axis is the sort of a stay-home population. So as you can see, there is a very strong positive correlation of this with respect to the load reduction. So, so as you can see that, in the very, very short term, the electricity sector is indeed going through some quite substantial changes. But, looking further longer term, I think, as we are getting out of this challenge and then going forward, I think, there are 3 key trends that are happening in the power sector. The first one has to do with the supply side. That is the massive decarbonization on the supply. And, this is something that is published by the National Bureau of Economic Studies. In the US, the power sector has always been #1 emitter of greenhouse gases. And between 2010 and 2018, there are 45% reduction of the power sector emission. So, power sector was famous for kind of moving things slowly, but looking at this number, I would say big things are happening in the power sector. There's it's nowhere close to declare victory yet, but I think there's significant things are happening, both in terms of retirement of the coal plant and also the installation of new gas and new renewable generations. So this is what's happening in Texas. It's interesting to note that almost half of the electricity in Texas is used in the residential, which is actually a very high percentage. And among the residential, almost half is devoted to just one thing, that is the air conditioning, because it's very hot. So we'll kind of allude that to some of the opportunities later on. On the second trend, I think it is on the demand side. That is, there are a lot of otherwise non-electrical loads that are being electrified as we speak. And if you ever pay attention to the stock market these days, you cannot miss the Tesla story now, right? Tesla, in fact, today they have just had a major wild run again today. And but that's only a small piece of the story. There's actually a bigger piece of the story, which is a lot of the industrial loads are also being electrified as we speak. So there are about 1 billion automobiles on this planet Earth, 1 billion. As of last year, there are about 5 million electric vehicles being sold. So you do the math. How much percentage is EV in today's fleet? About 0.5%, right? So 0.5%. Let's say even 0.5% goes to 5%. That's a 10 times increase, right? There's a major change on the electricity side. Now, is the grid ready? I'm not sure. Question that you can think about for yourself is how many EV charging does it take to blow up your sort of a local substation transformer, right? And this is not even those aggressive supercharging. These are the type 2 charging, right? These are the 8-hour kind of a charging. Unfortunately, the answer may not be very high. It might be on the order of 100 to 200, right? So there's a lot need to take care of the grid as all these things are happening. And that refers to the third trend, which I think, what I refer to as digitization. By that, I mean the proliferation of sensing, communication, computing, and algorithm devices that is happening on the power grid. So our research goal is that how do we, enable all of this digitization to allow for flexibility at all scales to manage this increasing uncertainty for a more distributed grid. And that really has been kind of the guiding principle that drives a lot of our research in the past decade. So I want to give you some stories about potential opportunities. In our group, we work a lot on this, digital, data-driven and digitized solutions, but we do it in a way that it is not purely data-driven. We do it in a way that we try to integrate first principle-based a understanding of the underlying physical models and trying to develop sort of value-added services. So in the interest of time, I'm going to talk about two stories, one on the opportunity side about utilizing digitization for demand flexibility, and then on the danger side about cyber attack. So, as we're trying to take care of all this massive installation of EVs and others, I think one of the biggest opportunities come from leveraging the customer end. And this is not a new topic. There's been lots of work on this topic, using a variety of different means of controlling the loads, starting from the idea of just directly load control, or to what economists liked about, which is, why don't we push down the real-time price to every single household? So every time when you start to cook, you look at the price of electricity. Or to a sort of a more benign and more kind of an implementable version on top of today's flat rate, such as price or incentive-based. And we thought that at the retail level, because as I was alluded to at the beginning, like in Texas, there are 50% of loads are just on the residential side. And then, if we want to leverage the flexibility from the demand, then we have to take care of this 50% of residential sector. And the residential sector are your house and my house and a regular Joe's house, which do not have a very strong automation and does not have a lot of sophistication on fancy software. So how do we still engage them without disrupting the state, the way they operate it today, right? So that has been driving our thinking in the past 5-6 years. There's some very interesting issues and properties of this kind of demand flexibility, because it is not always that you want this demand flexibility. You really only need it at a few fraction of hours in the rush hours, right? And then what's interesting during those rush hours is that even a tiny bit amount of reduction, let's say from Texas, would have meant a lot of savings and societal benefit for the entire system, right? What I'm showing you here is the supply stack in ERCOT. What we found is that even a 0.18% of reduction of the total load at that peak hour would have reduced the entire system price by $50 per megawatt hour, right? So the good news is that you really don't need to do too much, but you really just have to do it in the right time, in the right way, to do this right amount of reduction, to have the biggest bang for the buck, okay? So we want to, we conducted this, what we call energy coupon experiment, which is trying to say, let's keep today's flat rate, but then we can still try to incentivize you through some other means. So that's the first thing, is that it's not a mandatory price, but it's some kind of what we call carrots, which is incentives. The second thing is, instead of utilities issuing this peak time rebate as traditional otherwise would have done, we are thinking of ways to engage the customer in a more effective way. So I'll give you a thought experiment. If I give you $2 versus if I give you a lottery ticket that has a 0.001% of chance of winning $2 million, how many of you are willing to take the $2 and how many of you are willing to take the lottery ticket, right? So it turns out that I would like, my personal choice would be option B. And it turns out that it's actually not just myself. A lot of people think like me. The reason is because it's something actually called the prospect theory, which is to say that, human beings, in terms of the expected return, these two options give you the same expected return. But if there's a small amount of payoff, then human beings actually tend to choose the one that is a bit more risky, right? And that's, I think, explains partly why, things like Powerball is so popular in this country and other places. So we try to leverage that as well. The third one is that instead of giving a fixed everyday 3 p.m. peak time rebate, that's traditional way of doing this, we realize that in the future grid, the so-called rush hour may be changing day by day. I'll give you a concrete example. Most of us who are trained as power engineer would have thought that, okay, a peak hour must be, 3 o'clock in the afternoon, right? But guess what? If you go to California ISO these days, the new peak hour, because of the increasing penetration of solar, is actually turning to something like 7 p.m. or 8 p.m. That's when the sun is set, and that's when people begin to go home and start doing their evening chores, right? So we have to actually think of a dynamic instead of a fixed time, incentivization. So all these three things combined: a carrot instead of a mandatory real-time price, a coupon rather than a fixed monetary rebate, and then dynamic information rather than a fixed time, is what we call energy coupon. Okay, we actually have done this in partner with a Houston-based load-serving entity, and we actually have conducted 2 years of experiment in the Houston neighborhood. So instead of going through that video, I'll just go to the key findings. So what we found is that there is actually a substantial change of load patterns as we desired for these active consumers. And then another very attractive feature we found is that it really reduces the equivalent dollars that utilities have to spend or the load serving entities have to spend to convince their customer to reduce equivalent of 1 kilowatt hour. And that's really very helpful for them to engage the customer to do this meaningful demand response. Another kind of unexpected side benefit was that all this data we collect actually turned out to be very, very helpful to do some other follow-up research, which I will not talk about too much in detail today. So just to give you some sort of an overview of what this experiment is about, we actually separated them into two groups, just like the way we do experimental, economics. We have a treatment group, and then there is a comparison group. Comparison groups are the ones that are not being exposed to this energy coupon, and then the treatment group are the ones that are exposed to this energy coupon. And then this is a substantial behavior change from the active to subject, this red curve, versus this treatment, these inactive subjects, namely the one that are not being exposed to this coupon, right? So there's actually a substantial reduction. What's interesting, which I will not talk too much about it in detail, is that there seems to be some kind of a rebound after this major Hurricane Harvey, because this was done in the summer of 2017. And this is really a key slide. If you combine all these three things together, what do we get? Now, there are already kind of a very popular and very well established ideas of engaging the retail residential customer for demand reduction. And the most commonly used ones are the ones called critical peak pricing, or peak time rebate, or something like that. What they do is typically they would define a fixed time of the day, and then they would define a fixed baseline. And if you reduce from that baseline, then you will get equivalent of certain times of your retail rate. So for example, this is one of the most famous studies was by Professor Frank Wallach at Stanford. They did that in Southern California. It turns out that in order to, among all these complexities, in order to convince a customer to reduce 1 kilowatt hour equivalent of electricity reduction, they would have to spend something like 368% of the retail rate. So if the retail rate back then was 10 cents, then the utility may have to spend 36 cents to convince a customer to get 1 kilowatt reduction, right? Whereas in this energy coupon experiment, it's nowhere close to declare victory yet. But based on the 2 summers studies so far, what we found is that by combining a incentive rather than a price, by doing it as a lottery instead of a fixed monetary, by doing it in a dynamic rather than a fixed time, we were able to reduce that by 7 times. So let's say if the retail rate is 10 cents, then the utility may have to spend something on the order of 5.8 cents to convince a customer to reduce 1 kilowatt reduction, equivalent reduction, right? So that's sort of a good news to the utility companies and load serving entity, because that is a good way of engaging the customer in a cost-effective manner, right? So that's one story, that we found that this voluntary, completely voluntary, incentive-based mobile app and weekly lottery-based energy coupon is able to see a substantial load shedding, and it can be observed for these active subjects in the treatment group. And it reduced the effective cost. And then there are some side benefits. For example, the one that I show you on this paper, one is actually able to do some low resolution data, namely the smart meter data-based non-intrusive load monitoring, which was also very interesting. And also we have completed a NSF I-Corps, which is a way of doing entrepreneurship based on a personalized retail plan recommendation in places like Texas. So now this is the story about the end users, the little guys. But we care about the big guys too, right? We need to make an impact on the wholesale level. So how could a system operator like ERCOT or ISO New England try to get these little guys bundled together and then still manage to do a wholesale level market dispatch with all these enormous uncertainties, and yet still have to satisfy a certain level of risk or reliability guarantees? Is it possible to do that? So we have also thinking a lot about that. Fundamentally speaking, this is a problem of a feed-forward decision-making with uncertainties, right? There are multiple stages in the power system decision-making, from day ahead to hour ahead to the real time, right? So, and the fundamental question here is, how do you manage and handle the uncertainties here? And typically there are sort of 2 hammers, if you wish, typically, common ways to handle this uncertainty. One is in the broader family of stochastic programming based optimization. So the idea is that I don't know how the customer would behave, so I'm going to try to minimize some kind of expected cost, right? But then that expected cost, by the word expectation, the implication is that you actually have to know something about the customer's uncertainty distribution, right? Are these customers behave like a Gaussian noise or some other kind of noise? So that's a prerequisite. And if you don't have that, then that might lead to overly optimistic solutions. On the other hand, there is also this emerging class of so-called robust optimization-based approaches to handle the uncertainty. So the key idea is that I don't know what's going to turn out, but let me think about the worst case. And then I try to optimize against that particular worst case. Now, what would be the worst case of human-based demand response? Maybe the humans simply don't respond. If we use that as the worst case, then do we kind of lose the whole point of engaging them? Are we being too overly conservative, right? So that's really some of the challenges that has been guiding some of our thinking about some potentially new approaches. And we are pleased to kind of report to you that there has been some very exciting work actually, starting from the mathematical programming community and now reaching to the power system community, based upon some key results from so-called the scenario approach. The idea is extremely straightforward, right? And it's extremely intuitive, yet the surprise is that it actually gave you some very rigorous posterior results, meaning when the rubber hits the road, when the system is about to dispatch, you can actually control exactly the desirable level of, say, loss of load probability or things like that. And the only thing they need is to draw samples from the historical data set, and then to know the samples for that. And that's the good news, right? Because we kind of now live in this big data world, and we are going to collect more and more data, and that's the that's what it takes to implement this scenario approach. So just give you some very quick overview of this idea. So let me first define what is the scenario approach-based decision-making problem. So think about you're making a decision against some uncertainty. That uncertainty is shown in this figure on the right, right? This is the sample space that uncertainty will be drawn from. And then this parameter is the realized uncertainty at each time of drawing the samples. So the scenario approach is nothing but just compute against each of the turnout of this uncertainty delta. Let's say in this case, you pick 4 samples out of this whole sample space. And then you make your best choice based upon these 4 samples you draw. And then that, if you're trying to do a minimization problem, then the one would be this epsilon delta, epsilon star, right? Now, the real question for system operator is that if I'm making a decision based on that, how much likelihood is that decision going to violate any of the constraints at the implementation stage, right? If I am doing this in a day-ahead market, how do I make sure that my dispatch for day-ahead market actually, when it comes to the implementation stage, is not going to violate too much of the transmission line limits, right? That's the way you think about the problem. So the good news is that you can define precisely that using this area in the red. So the area size in the red is exactly the probability of violation of the constraints. So the exciting part is that you can actually show that there is a one-to-one mapping between the samples that you draw and this risk that at ex post stage is the likelihood you're going to violate any of the constraints. So in a kind of a very intuitive sense, it's almost like the system operator has a knob, and that knob is turning on the size on the sample, and that in turn gave the system operator an exact predefined risk parameter epsilon, and that risk is going to guaranteeing the ex post, meaning the post dispatch level of probability violation on any of the constraints. So that's very desirable for power systems, right? Because it's a safety critical system, and this is the way you kind of formulate the problem. So basically, you can think about the demand response as this uncertainty set, and then you're just trying to draw this human-based demand response from the historical data, and then you say, okay, based on this, what should be the best bet, best dispatch for all the generator as well as all the demand response providers. And this is a small sample system that to show that this indeed is guaranteeing the posterior level of probability violation. But that's only a 3 bus, right? So we are not interested in 3 bus. We're interested in 3,000 bus. So what's going to happen in the 3,000 bus system? The bad news is that the traditional theory is not going to work because it's not very scalable. The number of samples will be extremely large. So here we are using a synthetic Texas grid developed by my colleague Tom Overby and his group. And if you do the vanilla version of the scenario approach, it's going to give you a large required samples in order to come up with any meaningful level of risk. So what can we do? It turns out that there's some very cool, further polishing of this idea. And the further polishing depends upon our understanding of the domain knowledge. So here's a question for every one of you. Can you tell me, for a large meshed transmission network like Texas grid or Eastern grid or Western grid, at any given moment, let's say we have 3,000 transmission lines, at any of the dispatch, can you guess how many of the lines are simultaneously binding? Meaning, can you guess how much percentage of these transmission lines are are carrying the maximum power flow? Is it going to be 10%? Is it going to be 1%? Is it going to be 0.1%? Can you guess? The surprising news is that it's close to less than 1% and around 0.1%, right? That's amazing, right? So the good news is that even though you have a very large mesh networks, but because of the way that system is designed and because of the way we run the contingencies, the percentage of binding constraint at any given dispatch is actually a very, very small percentage of the lines. What that means, theoretically speaking, is that it actually reduces the so-called support constraints or the support scenarios of this scenario approach, and that in turn gave you a much reduced number of samples needed in order to guarantee a desirable level of risk. So I'll give you the same example: 3,000 buses, and by utilizing this property, one only needs to take about 870 scenarios in order to guarantee a theory of less than 0.005, less than 0.5% of probability violation. Okay, so that actually becomes very scalable in the real world power grid, and we are kind of very happy about that. But what I'm showing you here is just really only one particular technology of handling uncertainties. If one take a step back and think about it, I think there are different kind of metrics and desirable performances that one could ask for such a digitized optimization solutions. For instance, do you care about posteriori economic efficiency? Do you care about a priori, mean ex ante economic efficiency? Do you care about computational efficiency, or do you care about reliability? And different toolboxes really offer you different kinds of flavors of which one they are better or worse off. So we try to give you a sort of a more comprehensive viewpoint of what it takes to arrive at this. Sorry. Can you see my screen now?
Yeah, we can see it now.
Okay, great. Thank you. So I just give you two stories. One is about engaging the customers. One is about how do you then turn that into a system level dispatch with some risk guarantees. Now, let's go to the flip side of digitization, some of the potential dangers of digitization. And I think, I don't have to motivate too much about that for CAMS subcommittee. I'll give you a concrete example, right? So one of the concrete example is that, in one of the hallmark success of control engineering in transmission level grid is this automatic generation control, right? Which is essentially a feedback control to keep the frequency checked whenever there's a mismatch on power balance, right? The way the AGC works is that you're observing the differences between the Thailand flows and frequencies, and then you decide what to do next. You give a feedback, negative feedback. One can easily think about a potential intruder who can just simply do changing from the negative feedback to positive feedback, and that little change of sign would have blown up the system eventually, right? So the question is really, among all these potential cyber attacks, how does one think about a more rigorous approach to actually detecting these cyber anomalies? The attacks could be replay, noise injection, or destabilization, right? But how could one kind of conceptualize all of these and think about a more rigorous way of detecting this? Again, it boils down to our understanding of the physical models. And this is really the starting point of this idea of what we call dynamic watermarking. So how many of you have heard about watermarking? It is like this, I don't know if you have ever watched this movie, Ocean's 11. Someone is trying to, rob the bank in Vegas. And, someone is basically replaying a normal day surveillance video camera to the control room so that the control room people don't see that anything happening, but they are robbing the bank, right? So, putting into this context, if the control room is smart enough to just inject a tiny bit of let's say a random noise, for example, just to put a little clock on the scenery and then give a random number to the clock, they would have detected that something is not right? So the same idea is applied here in the context of dynamic watermarking. What we try to say is that at every time when the AGC is actually giving the control command to the generators, in addition to the regular command that you would have generated, why don't we just add a little private noise? That private noise is so small that is in the vicinity of almost like the white noise, right? But it's a private signal. And that private signal, because we know that the physical power grid has an electromechanical transfer function, one can actually then calculate how this private signal would propagate throughout the grid and then come back to the control center through the sensors. So the research question becomes, if one can characterize this private signal E of I's connection with the observation that you get from the SCADA Y of I, then one can actually have a one-to-one mapping of guaranteeing that system is not being compromised. And it turns out that this actually has some very fundamental connection to one of the hallmark success in statistical signal processing, the Kalman filtering. And these two conditions are sufficient as well as necessary conditions to guaranteeing that the system sensors are not being compromised. And practically speaking, checking on these two conditions can actually be implemented by extremely rudimentary arithmetics. It turns out it is just a bunch of addition, multiplication, and matrix multiplications. So that's the good news, that this can be done in a streaming fashion. Right? So, want to show you a case study. This is a 4-area power system in which the AGC is doing its job. With the blue signal, the blue color is the actual signal, and then the red color is the signal with injection. And as you can see that, one of the earlier concern that some of the vendors were having to us was that, well, if you add this dynamic watermarking, are you going to increase the wear and tear cost? The good news is that if you look at the red and blue, they're almost in the same ballpark in terms of the wear and tear to the generator, so not much. And but that red signal contains that little private signal that we just talked about. So I want to show you a case study. This is a sort of just a destabilization attack. As you can see, the system eventually got blown up, and the over frequency relay caught that at the minute of 18, where the attack started on minute 10. So if you're a very experienced power engineer, if you take a look at this, and you might say, well, at minute 10, looking only at the left curve, it will probably be very difficult for me to eyeball that attack, whereas its indicator function would have easily picked that up. And what you see here now is a more sophisticated attack. This is actually a induced kind of an oscillation, inter-area oscillation that attackers are engineered. One would have never been able to detect that is actually a cyber intrusion, whereas this indicator function was able to successfully detect that. So the good news is that this actually can be fairly generalizable in both transmission as well as distribution grid. In fact, we are now working with the Department of Energy CETO office for a large grant focusing on developing this technology for distribution grid with large solar generations. So I talked about some opportunities from using digitization to increase the flexibility. I also talked about some potential cyber intrusion dangers. I want to kind of end my talk with some remarks about going beyond just technologies. there's actually, given the complexity of this industry, it's very important to develop appropriate market and regulatory framework to align, all these technological innovations with the real world implementation. So for example, right, we're talking about demand response. There's actually some very cautionary note that I wanted to share with you regarding standalone demand response providers. And that cautionary note is that if we allow the existence of standalone demand response provider, namely you and I can start a company and we can do demand response, then the ISO will be facing a fundamental problem of revenue inadequacy. What does it mean? It means that there's not enough money on the table for the ISO to clear the market. Why? This can be very easily explained through this very simple conceptual example. Suppose there were no standalone demand response provider, DRP, if there were only one load serving entity and one generation company, the money flow is easy, right? Whatever generation get paid is collected from load serving entities. And even if the system has congestion, there's only going to be the revenue, extra revenue rather than revenue inadequacy. But if there is a company that declares that they're trying to reduce the demand and they would like to claim the credit for doing so, then you run into this issue of, physically you are clearing, X amount of megawatt, but this demand response provider is asking you to pay for this shadow reduction that they have reduced from this otherwise benchmark or otherwise baseline. And that creates this revenue inadequacy. And I thought that's actually a fundamental issue in the market design that one needs to take a look at. Also, from the ISO perspective, how could one think of a way of engaging all of these uncertain and dynamic resources in a decentralized manner where still allowing the information discovery and exchange through the notion of prices, right? So one, this is actually another paper we did a couple of years ago. The key idea is that today's locational marginal price is fundamentally based on the byproduct of a deterministic, static supply-demand optimization problem. And that is not going to be appropriate and enough to allow for the system to discover that true social welfare. In fact, there will be a large amount of social welfare loss if we were to follow that price. So it turns out that this is actually a very difficult decentralized stochastic control problem. But again, there's some very interesting things that come into rescue. And that is if one allows for this a positive and negative states, namely if there is a sort of a pervasive notion of energy storage, namely everybody becomes not only a producer, but actually a prosumer, then the problem becomes actually very scalable and one can develop such a decentralized control via dynamic stochastic prices. But then again, how do we translate that into regulatory and implementational framework? That's a different question, right? So there's actually a substantial value of energy storage from that perspective, namely achieving a better social welfare outcome. So, and then there are more challenges such as how do you regulate cybersecurity? Who should pay for cybersecurity enhancement? How do you incentivize the infrastructure enhancement for these EVs, right? If my neighbor bought a Tesla, should I be paying for that wire expansion? And how do you translate all these cool gadgets, power electronics, digitization, supercomputer, all of these towards something tangible and valuable for personal electricity services, right? So to summarize, I offered you a viewpoint of where the grid is going. I talked about some stories about engaging end users to provide flexibility, which then in turn can be utilized for scenario-based risk-tunable dispatch. I talked about the potential challenges or dangers of cyber security and how dynamic watermarking could be used as a rigorous way of detecting those cyber attacks. I also suggested some issues with aligning market and regulatory framework to achieving the full potential of digitization. And I think, having communities talk to each other is really the key to success of this. So with that, I would like to end my talk and thank you for your attention.
Thank you, Professor Xie, for the very comprehensive discussion and the directions on the topic of massively digitized power grid. So we have around like 35 audiences today, and audiences, if you have questions, you can use the chat function to type in the chat window so that I can ask it for you, or you can raise your hand and I'll invite you to unmute. So Professor Xie, so I'm impressed by the way how you detect cyber attacks in the system. And I do have a question for page 47, where you show the comparison of eyeball detection versus the algorithm detection. You can see that on right-hand side, the values from the matrix have quite small values from 0 to 6 times 10 to the negative 10 to the negative third. So how can my question is, how robust is this algorithm to measurement noises and parameter errors? Has this been considered?
Thank you for your question. Yes, this is a very good question. Indeed, in the first, so what I'm presenting here is already like, 18 or 12, 24 months old result. So back then, the noise that we considered was a simulation-based noises, and it was fairly robust against those. Now, in the past 24 months, we actually have made substantial headways. We actually have developed a hardware in the loop test bed in the lab, and we are able to feeding some of the real world center point energy based measurements to that and detect the result very robustly. So as of now, we are actually, pleasantly surprised to see the result has been very, very robust. In fact, we are trying to find out a way or a particular case where the result is not so good. So far, okay. We haven't found yet. Yeah.
Oh, it's great to hear. Thank you for the explanation. So let's see if we have other questions from the attendees. Attendees, you can raise your hand, or I see. Okay, raise your hand. And yes, Mr. Jim Straight, please unmute yourself.
Yes, I have a question. So who will be held accountable if there is a successful, serious cyber attack on the North American power grid?
I think that's a good question. As any of these, issues goes, there's something that engineers can answer, and there's something that engineers cannot answer. I'll tell you what I can answer, and then we can talk about other things as well. I think what engineers can do is, can we identify such attack? Can we actually locate where the attack came from? Can we also then try to classify what kind of attack it is? I think those are the things that the engineers, PES community can do. Now there are something that perhaps is beyond the engineers' expertise, which is who should be held accountable. Given the complexity of this industry, it's not exactly clear to me who should be eventually held accountable. Of course, one could argue that NERC, who designed this cybersecurity requirements, and utilities who are the owners of this infrastructure, would be held accountable. But it's a very complicated space. I think. This is a very good question. I think there are something that technology have yet to accomplish, and that's what I'm trying to focus on right now here. But I think there's also much more, institutional and legal implications, which I'm not talking about here.
Okay, thank you for your answer. The reason I ask is that there seems to be a lack of transparency in the power industry in general. For example, the availability of funds expended to ensure cybersecurity. You know, the dollar amounts don't seem to be readily available anyway. That's the only question that I had anyway. Thank you.
Mm-hmm. I mean, that's a very good question, and I would perhaps argue that some of that is perhaps for good purposes. Just like you may not know exactly every expenditure of Department of Defense, but again, that's beyond. I think that's beyond the scope of this talk. Yeah.
Okay, we have another question from our guest, RBAH, and the question is, what is the role of blockchain technology in digitization of power systems? What is your prediction of using blockchain for energy markets in the near future?
So this is a very popular question these days. Thank you for your question. I think I'll give you some easy answers and I'll give you some harsher comments. I guess the easy kind of first thing to do is that, blockchain is a very nice way of doing bookkeeping, right? It's a secure way of doing decentralized bookkeeping when there is no centralized ledger. So it certainly can, one can certainly see potential applications in places where there is not a strong centralized system operator, right? Some remote area, or as people are beginning to talk about peer-to-peer energy transactions, that's, I think, a easy place to be adopted. I don't know if blockchain is going to prevail in today's wholesale level market, not because that, it's not a good technology, just because I haven't found a good connection to that yet. So this is my honest feeling. But nevertheless, I think it's promising and worth looking into. In fact, under the jurisdiction of Big Data Subcommittee, we have just approved a new task force on this very topic, on blockchain and their implications to power grid. So if you're interested, please reach out to me and I'll be happy to connect you to the task force.
Thank you. And we have a question from our chair, CAMS chair, Henry Huang. Henry, can you mute yourself? Unmute yourself.
Hey, thank you, Hantao. Hey, I want to first of all thank you for two things. One, of course, is thank you for the wonderful talk you gave today. Another one is actually thank you for your success in your Big Data Subcommittee webinar series, which inspired us to copy what you have done and then making our own series. So again, thank you for that as well. Now you're contributing to this today as well. So thank you for all that.
Well, you're very kind, Henry. Thank you.
You have a lot. I guess that you provide a lot of information today. I need to take more time to digest all the details. I have one question, just following what been discussed earlier about this watermarking. I think this is a great idea of using watermarking for ensuring cybersecurity, kind of reminding me of some other ways people do watermarking, like in the software coding, they inject like a random grammar mistakes, so to secure the copyright of the software codes, right? So then if they want to say detect whether someone is stealing the code, they can just detect that they have the same kind of grammar mistake in the codes. So my question is, how do you compare your watermarking with that software coding watermarking? I see you also injected like a random noise, which is kind of like injecting the random grammar mistakes into the coding. Is it comparable, or is it somewhat very fundamentally different? And what do you need to design the signal you inject? And do you need to secure the design so no one can copy and actually remove the watermarking so they can actually still causing cyber issues?
So thank you very much for this very insightful comparison and comments. And I would like to say that the difference is in the first word, dynamic. So in the software industry, there is no such notion as dynamic. By that, I mean, you have a software, you put a watermark, and then whoever is violating the copyright, you can detect that because there is a random grammar error. What is very unique and different, and perhaps also to our advantage in the power grid, is that the power grid is fundamentally a dynamical system. By that, I mean, when you're injecting a control command at the generator, that control command will then eventually propagate throughout the entire system and then get reflected back from the SCADA sensor reading that you collect, right? It's a kind of an engineer, we like to talk about transfer function, right? It's a transfer function relationship between the input and output rather than a static relationship. So that actually gives us a great advantage. That's why we call it dynamic watermarking. What that means is that, we can actually give to the world. We can tell all the attacker, hey, listen, I'm going to inject a private signal now at generator 1, and the private signal has a mean 0 and then the standard deviation of 0.01. I can tell you exactly that. You are still not able to replicate that system for me because of this, of the knowledge of the system transfer function being controlled at the control center. That basically is the key of relating the function E of I with the function Y of I, the Y of I here being the output and E of I here being the input. That's the E of I is the dynamic watermark. So the good news is that we can actually be more forceful and more, we can even tell the attackers that, hey, we are going to start this watermarking exercise. Yet they still are not able to fool us around because of our knowledge of the physical grid transfer function. Now, if the attacker knows exactly the power grid dynamic transfer function model and knows exactly what private number we are injecting at time 0, at time 1, at time 2, at time 3, and so on and so forth, they might be able to fool us. But that likelihood is very, very, very small, right?
Excellent. Thank you, Laura. I think this is, again, a great idea.
Thank you.
Thank you all for the questions and answers. Any other questions? We are close to 1 hour since the start of the webinar, and I think today's webinar has been going very well. So if there is no more questions, I think that's all for today's webinar, unless Professor Xie has other information to announce. Oh.
No, if you have any further questions, please feel free to just shoot me an email, and I'm happy to also connect you with, big data subcommittee, the sister subcommittee that CAMS is doing. I think I'm really glad to see that we are, helping out with each other and promoting each other, and it would be indeed great to see that our community is getting into this new mode of normality and perhaps even amplify our interactions.
Great. Thank you very much, Professor Xie, for today's presentation. And thanks to every participant for joining our webinar today. So future webinars will be posted on the CAMS website, and please stay tuned. Goodbye.
Thank you. Bye-bye.
Thank you again, Laura.